How do physicists know which particle is which after a particle collision? How can you tell an electron from a proton in practice? After all, you can't really just look at them and say, hey, that's an electron. In fact, physicists look at how particles bend as they travel through a magnetic field. In early times, they allowed the particles to travel through a near vapor made from alcohol and water. The particles would create little bubbles where they boiled the solution, and the scientists would photograph the track of bubbles. Now more modern detectors are used, but the idea is the same. Particles with charge feel forces in a magnetic field and are steered in paths that depend on their fundamental properties. The basic equation for the radius of motion of a charged particle is simple. The radius of motion can be calculated as the momentum of the particle divided by the product of its charge and the strength of the field. Let's talk through how that works. First of all, the direct proportionality to momentum makes sense to me. An object with more momentum is harder to steer. This is essentially a statement of Newton's second law. So, the more momentum a particle has, the higher its radius of motion should be. Momentum at low speeds can be thought of as the product of mass and velocity, so higher mass objects have higher momentum. As you approach the speed of light, the momentum becomes rapidly higher, approaching infinity at the speed of light for a particle with non-zero mass. So we'd expect more massive particles to trace out bigger circles. Let's see if that happens. Let's hit play and watch the path of an electron. The radius of the electron's motion is about 7 millimeters, not very big. Now let's change to a proton. Since it has an opposite and equal charge, it should circle in the other direction. But its circle should be much bigger because it has a lot higher mass than the electron. Let's check it out. Now we see the radius of the proton's motion, about 13 meters. Much higher, by nearly a factor of 2,000. In fact, keep a close eye on the radius measure in this simulation. We use scientific notation because the values range so widely. So the mass of the particle tells us a lot. The radius of the curved motion is much higher for higher mass given a certain speed. The track tells us about mass, but does it tell us more? Notice that we went from a negatively charged particle to a positively charged one, the direction of motion flipped. This has to do with the magnetic force, which acts at right angles to the velocity of a particle. For positively charged particles, I use the so-called right-hand rule to determine the direction of the force. But for negatively charged particles, I switch it up and I use the left-hand rule instead. More charge means more force. The two are directly proportional. And more force means a smaller radius. So particles with more charge will curve into circles with smaller radius. A good example of a particle with unusual charge is the delta++ baryon. If you apply a stronger magnetic field, you'll also get a stronger force, and so a smaller circle. This means if you know what type of particle you're looking for, you can get the magnetic field in the right ballpark and not lose the particle. Since the momentum of a particle is easier to calculate at low speeds than high speeds, we provided a graph at top left of momentum versus speed for the particle you have selected. Keep a close eye on the units on the vertical axis. The values change so radically by particle type and speed that you need to watch the scientific notation to make sure you're really getting the data. The graph at right shows the radius of motion as a function of momentum. Again, keep an eye on the units on the axes, as these will vary enormously by particle type and momentum. So you can play around with all the parameters here. You can adjust the type of particle and its speed as a fraction of the speed of light. You can adjust the strength and direction of the magnetic field. You can also show the velocity and magnetic force vectors to practice up on your right-hand rule skills. Thank you for watching.